Hey, Physics 30s. Okay, we're going to talk about the problem with the Rutherford and Rutherford's model. So Rutherford, remember, did his gold foil experiment. He shot alpha particles at gold foil. He watched the alpha particles mostly stream on through, but some of them deflected like crazy in all sorts of different directions. So he concluded that his model, Thomson's model, was incorrect with the plum pudding and the fluid appositiveness, where now he just concentrated all of that positiveness down into a small nucleus, which is really, really small in the femtometers, and the rest of it is 100,000 times larger of empty space for the total atom itself. So remember, the atom is included right to the very last shell of electrons, and the nucleus being right in the very center. Okay, there's a little discussion about the size of that. Okay, so one problem with the Rutherford's model was that those electrons were moving in a circle. Okay, so there was a guy that said that if electrons move in a circle, then they should be accelerated, because if they move in a circle, they're changing direction. And to change direction, you have to accelerate. So there was a scientist way back in our day, 2 or 3 chapters ago, that said that if a charged particle accelerates like an electron, then it should do something. What should it do? Well, it should release radiation in the form of EMR. That accelerated charge, or decelerates or accelerates, doesn't matter, will release energy in the form of electromagnetic radiation. And if it does that, as it continually accelerates around, it's releasing this energy, and it gets slower and slower and slower, and then it just collapses in on itself. Is that what happens? Am I here? Right? I haven't collapsed into myself. And if all these electrons were to collapse into the center, really nice looking today, they're all to collapse into the center, then I would just be a pile of atoms. I wouldn't be able to hold myself together. My hands would just fall apart. None of these bonding electrons that are shared between covalent bonds and ionic bonds would exist. And we would just be nothing. Everything would be dust. Nothing would hold together with anything else. Everything would just collapse, and everything would be neutral, and that's it. All right, we wouldn't exist. So obviously that's not true. So there was a problem. That's one of the problems. Maxwell says that accelerated charges produce EMR. So we've got to fix that. Okay, so a guy that fixed it is Bohr. Bohr decided to fix it by just saying one thing. If the electrons are in a very specific energy shell, then they just don't release energy. They break the rules of physics as long as they're within their energy shell. But if they move between energy shells, that's when they can absorb or release energy. Okay, so they're still moving in circles, but if they're inside that shell, that very specific distance away from the nucleus, and we'll talk about the different distances that they could exist in when we talk more in depth about his model. But if they're inside those shells, the rules of physics don't apply for the electron. They no longer release energy, and the atom is now stable. So that's the Bohr model, right, in a nutshell. Another thing that the Rutherford model could not explain was this thing called spectrums, right? Why do excited gases only produce light of certain colors? Or conversely, why do they only absorb certain frequencies? Okay, so if you haven't done so, pause the video and watch my demonstration on electromagnetic spectrums from excited gases. You just see it, they'll probably just say demonstration of EMR spectrums. Okay, let's go watch that, come back, and we'll talk a little bit more in depth. So hopefully you stopped or paused this video and did that, or you already watched it, who knows. So that's one thing. Another thing that I couldn't explain, we already talked about this idea that they should give off energy continuously. That's what Maxwell said. Another thing they couldn't explain is, why is everything just so nicely organized in the periodic table. Why do certain chemicals like helium, xenon, argon, why do those chemicals all act the same way? Why do fluorine, borine, and all those other things, why do they all act the same way? Why are gold, silver, and those transition metals, why do they all do that? Right? Well, this classical model, this orbital model, just doesn't make sense in those kind of things. They should all have these distinct characteristics. So we have to modify our model a little bit to explain for these three things. And this is where Bohr comes into. Okay, so let's talk about the spectra first, the excited gases and the gases absorbing certain types of lights. So this middle one here, the bold part. So to understand this spectrum, so most of the time we're going to talk about hydrogen because hydrogen is one of the simplest gases out there. It just has one proton, one electron, it has one neutron, but that doesn't really change too much. You can have one with no neutrons or two neutrons, different isotopes. But they do have the one electron and one proton. Because of that, it has probably the easiest looking, simplest looking energy shells. And that's why we're going to look at it more often than the other ones. It's easier to understand what's happening when you only have one electron and one orbital in the valence shell. Okay, so, so there are three types of spectrums that we're going to talk about. The first one is the easy one. It's a continuous spectrum. Now, how do we produce a continuous spectrum? Much like this little rainbow here, that's a nice continuous spectrum. There's no holes in that one. Well, we produce a continuous spectrum. I'm just going to zip down here a little bit by just heating up a solid or a liquid, not a gas. It's going to heat up a solid or a liquid. So if we heat up a solid or a liquid, it'll just glow white hot or red hot or whatever. If you pass that light that it produces through a diffraction grating such as this, right? Through a diffraction grating. Now, I'm going to put this over here. If I put that through a diffraction grating, you're going to produce a spectrum there. You can kind of see a little rainbow around my Batman head, okay? And that spectrum, as long as it's coming from a heated solid or liquid, should be a continuous spectrum. So the spectrum from the sun, let's just say that. The spectrum from the sun is a nice continuous spectrum. It has all the wavelengths of the rainbow, ultraviolet, infrared, all sorts, all different directions, all the way from gamma down to radio waves. So it's producing this whole nice continuous spectrum for us. Now, don't get confused. The sun, as it comes to us through our atmosphere, is not a continuous spectrum. It looks continuous. The sun does look like a kind of white ball up there, right? Maybe a bit yellowish because of some refraction of the blue light away from it. But it's not continuous. Don't get confused about that. There are holes in that spectrum, right? And the spectrum that has holes in it is called an absorption spectrum. Now, to produce an absorption spectrum, we take the continuous spectrum that we get from a hot, solid, or liquid like this, right? We take that continuous spectrum and then we pass it through, right? Just go down here a little bit. We pass that through an unexcited gas, like our atmosphere or a nebula out in deep, deep space, or the gas in a light bulb or something like that. Pass it through that gas, the gas will absorb some wavelengths, not all the wavelengths. According to classical physics, it should just absorb it all. It absorbs all the wavelengths, done, you got it. We'll show you all the different models and how they differ from what you think they would happen and what actually happens. But according to classical physics, if all I have to do is just move my electron up a shell or up away from it by just giving it any form of energy. So if this was Rutherford's model, it would just absorb all light and then just release all that light in all different directions. It would just be chaos. So obviously that's not true. So it's only going to absorb certain spectrums, not all of them, only very particular ones. And we'll talk more in depth when we talk about the Bohr model. But this is how you create an absorption or a dark line spectra. Take that continuous line or the continuous rainbow that we had, white light, pass it through an unexcited gas, and what you get is these kind of holes. Where'd that one go? Lost it right here. you get holes in the spectrum. Now, the holes are just where the electrons absorb to move to the next energy shell. Okay. We'll talk about why there's big gaps there too later on. Okay. And the last type of spectrum is the bright line spectrum. So you can see bright line spectrum. The bright line spectrum is, if you look at how they match up, so look at the bottom two here, Mercury and the Mercury bright line spectrum, the Mercury absorption spectrum, you notice they match up perfectly. The light that Mercury would absorb is the exact same light that Mercury will emit if you excite it. So you would excite the mercury gas. Or you just excite any gas, it doesn't matter. So in the demonstration that you saw, I excited helium, nitrogen. I do have mercury too, but I'm not going to do that one. And a couple other ones I did, neon, sorry. So when I excite that gas, it will release only the lines that technically it would absorb. Right? And we'll talk about why that is when we get to the Bohr model in depth. So the Rutherford model could not explain this. So let's go through how we get those again, because I could ask this kind of easy question. Okay, so to get a continuous spectrum, you heat up a solid or a liquid, so that'll produce the whole spectrum. To get a bright line spectrum, you excite, heat up, pass electricity through, do a few things to a gas. You excite it, it will release light of just certain lines, certain bands from that, just of we call the bright line spectrum. Another thing about that, every element has their own bright line spectrum. So when we saw neon, most of the lights were over here in the yellow and orange range. If you look closely, you can't really see them in there. They're really dull, but there are some green and blue lights in there too. Most of the lights are going to be on this side. Okay, and then the dark line spectrum, right, would be if I take that continuous white light spectrum of everything, pass it through a gas, the gas will absorb the same wavelengths that it emits when it's excited. And so you get this line here. Right? Now this bottom one here is called the Fraunhofer lines. So this is, these are the lines that you see after the sun passes through our atmosphere. So if you're on the other side of the atmosphere, this would be a continuous spectrum. The sun does release a nice continuous spectrum. This is just a heated ball of molten gas and liquid and solids up there. Right, so it's just producing this nice continuous spectrum for us. But once it passes through our atmosphere, it becomes a dark line spectrum. So that's very important. That what we see on Earth is not a continuous spectrum. It looks like it. It looks pretty good. Like if you were to look at this with the naked eye using a diffraction grating, wouldn't recommend that, but if you were to do it, it would probably look pretty continuous. But there are dark lines in there. You can kind of see that. And all these little dark lines here, they all line up to chemicals that are inside our atmosphere. So if there's hydrogen, sodium, neon, mercury, if these things were in our atmosphere, these lines here would be in here. I don't know if maybe mercury could be in there. Let's see. It doesn't quite match up perfectly. But all these lines constitute like a fingerprint of a different chemical that's inside our atmosphere. It's pretty cool. So that's how we can use these spectra to determine what is the gas that, when I can't remember what the Finger of God nebula is. It's a special one. So it's a pretty big nebula. It's called like the nursery of stars. But it's just a bunch of gas in space, and light is passing through that nebula. By looking at the spectrum that it absorbs, we can determine what's inside that nebula. Or same as what's inside the atmosphere, our atmosphere, the atmosphere of different planets. We just kind of look at the spectra that it produces if light were to pass through it. It's pretty cool. All right. So why is this exciting? And we'll talk about that in the next video because we're at the 14-minute mark for this one. And I'll see you then. Bye.